June 1940. The skies over Britain are about to become a graveyard. Nazi Germany has conquered France in 6 weeks, and now Hermann Göring's Luftwaffe is staring across the English Channel, preparing to obliterate the Royal Air Force. The Spitfire, Britain's technological marvel, should be the perfect weapon to stop them. But there is a problem, a fatal problem. The British government, trying to save money, has fitted their fighters with wooden propellers designed in the previous decade. Meanwhile, every German Messerschmitt pilot is flying with American technology that makes their aircraft climb faster, dive harder, and kill more efficiently. The British pilots know they are about to be sent into combat with one hand tied behind their backs, and the man who could save them, an American engineer named Frank Caldwell, has been sitting on the solution for 7 years. But this is not just a story about the Battle of Britain. This is the story of how one engineer built a gearbox inside a spinning propeller, unlocked 1,000 horsepower that nobody could use, and changed the course of the Second World War. And almost nobody knows his name. To understand what Caldwell did, you need to understand the problem he was trying to solve. Imagine trying to win a drag race in a car that is stuck in 4th gear. The engine screams at maximum revolutions, but the wheels barely turn fast enough to gain speed. You burn out the clutch before you even reach 30 miles per hour. The raw power is there, thrashing inside the engine block, but you have no way to put it down on the tarmac. In the 1930s, this was the reality of aviation. Engineers had built massive 1,000-horsepower engines, but they had no way to put that power into the air. Throughout the 1920s, propellers were brutally simple devices. They were twisted pieces of wood or metal, bolted directly to the engine crankshaft. They were rigid. They were unchanging, and from an engineering perspective, they were an absolute nightmare. The problem was something called angle of attack. Think of a propeller blade biting into the air like a screw biting into wood. If the blade is flat, what engineers call fine pitch, it takes small bites of air. This offers low resistance to the engine. The engine can spin up to high revolutions per minute very quickly. This is perfect for takeoff, when you need maximum thrust to get off the ground. It works exactly like first gear in a car. But here is where the nightmare begins. Once you are flying fast, those small bites become completely useless. The engine hits its red line, screaming at maximum revolutions, but the plane will not go any faster. You are revving the engine to destruction, wasting fuel, and going nowhere. So you twist the blade more steeply. Coarse pitch. Now it takes big bites of air. It pushes a massive volume with each rotation. This is perfect for cruising at high speed, like 5th gear in a car. But if you try to take off in coarse pitch, the air resistance is so monumentally high that the engine cannot reach its power band. It stalls. The plane bogs down. You crash at the end of the runway, if you even make it that far. For decades, designers compromised. They built medium-pitch propellers that split the difference. And these propellers were terrible at everything. They were sluggish on takeoff, choking the engine when you needed maximum thrust. They were slow at top speed, never letting the engine reach its full potential. By 1930, engines were getting bigger and more powerful. 500 horsepower, 600, 800. But the planes were not getting much faster. The fixed propeller was wasting 40% of the engine's potential energy. It was creating drag instead of thrust, actively fighting against the very power it was supposed to harness. Pilots were trapped in a mechanical cage, and the key to that cage was sitting in a small office in Connecticut. Frank Caldwell was the chief engineer at Hamilton Standard Propeller Corporation, and he was obsessed with efficiency. Not in the polite academic way that most engineers talked about fuel consumption at conferences. Caldwell was genuinely angry about wasted power. He would walk past aircraft on runways and see engines screaming at maximum revolutions, burning fuel, and producing almost no thrust. It drove him mad. He knew the solution was simple in concept. The pilot needed to be able to change the angle of the propeller blades while they were spinning at full power. But the execution was anything but simple. Think about the mechanics of what he was trying to achieve. The propeller hub is spinning at 2,000 revolutions per minute. At that speed, the centrifugal force trying to rip the blades out of the hub is roughly 20 to 40 tons of raw mechanical violence. Every single rotation. And Caldwell needed to build a mechanism that was delicate enough to twist a blade by exactly 2 degrees, precise enough to hold that angle under combat stress, and strong enough to resist 40 tons of force trying to tear the whole assembly apart. How do you build something that can do all 3 at the same time? Most engineers tried to use gears and mechanical linkages. They failed. The systems were too heavy, too complex, and they shattered under the stress. Caldwell looked at the problem differently. He did not use gears at all. He used hydraulics. He designed a propeller hub with a sliding piston inside it, and he used the engine's own oil pressure to move that piston. By pumping oil through the hollow center of the crankshaft, he could push the piston forward or pull it backward. Connected to that piston were mechanical linkages, counterweights, and cams that were attached to the root of each blade. The system was elegant in its brutality. When the pilot pushed a lever in the cockpit, oil rushed into the hub under high pressure. The piston moved. The linkages rotated. The blades twisted. Fine pitch for takeoff. Coarse pitch for cruise. It happened in seconds, smoothly, while the propeller was spinning at full power and the engine was roaring at maximum revolutions. Caldwell had built a gearbox inside a propeller, a hydromechanical marvel that could shift gears in mid-air without the pilot ever taking his hands off the throttle. But the aviation industry was deeply skeptical. They said it was too heavy, too complex, too many moving parts, another fragile component that would break under combat conditions, leaving pilots stranded with a seized propeller and a screaming engine. Caldwell had the solution to the biggest problem in aviation, and nobody wanted to buy it. Then, in 1933, Boeing built a plane that was about to change everything. The Boeing 247 was supposed to be the first modern airliner. All metal construction, retractable landing gear, 2 powerful engines. It was designed to fly passengers over the Rocky Mountains, connecting the east and west coasts of America faster than any aircraft in history. Boeing had spent millions on development. United Airlines had already placed orders. This was the future of commercial aviation. But during testing, Boeing engineers discovered a horrifying truth. The plane was too heavy. With fixed-pitch propellers, the engines could not generate enough revolutions per minute to lift the aircraft safely out of high-altitude airports like Cheyenne, Wyoming. At sea level, the 247 performed reasonably well, but at 6,000 feet, where the air is thinner and engines struggle to breathe, the fixed propellers choked the engines before they could reach their power band. The plane would lumber down the runway, burning fuel, and barely get airborne before running out of space. Boeing had built a turkey. They had poured a fortune into an airliner that could not operate on half the routes it was designed to fly. The company was facing financial catastrophe. They were about to scrap the entire project. Frank Caldwell showed up with his controllable pitch propellers. Boeing had nothing to lose, so they bolted them onto a 247 and ran a test flight. The pilot set the lever to fine pitch for takeoff. He opened the throttles. The engines screamed to full revolutions immediately because the blades were offering minimal resistance. The propeller was biting the air with small, rapid chunks, exactly like first gear in a car. The Boeing 247 leapt off the runway in half the distance it had needed before. The transformation was instant and undeniable. Once airborne, the pilot pulled the lever to course pitch for cruising. Oil pressure shifted inside the hub. The blades twisted to a steeper angle. The revolutions per minute dropped, but the speed increased dramatically. The plane cruised over the Rockies effortlessly, maintaining altitude and speed with power to spare. What had been a struggling, underpowered disaster was now the fastest airliner in America. Caldwell had not just saved Boeing. He had saved the entire 247 program and proved that his hydraulic system worked under real-world conditions. But Caldwell had done something far more dangerous than rescue a commercial airliner. He had unlocked the cage. Suddenly, engine designers realized they were no longer limited by the propeller. They could build massive, high-compression monsters. 2,000 horsepower engines, 3,000 horsepower engines, the kind of brutal power needed for war. Because now, for the first time in aviation history, they had a way to actually use that power without tearing the aircraft apart. In 1933, Hamilton Standard and Frank Caldwell won the Collier Trophy, the most prestigious award in American aviation, for the development of the controllable pitch propeller. President Franklin Roosevelt congratulated Caldwell personally at the White House. Across the Atlantic Ocean, Germany was watching very closely. In Great Britain, the Royal Air Force was designing a fighter that would become a legend, the Supermarine Spitfire. It had the perfect aerodynamic shape, engineered by Reginald Mitchell, to cut through the air with minimal drag. It had the Rolls-Royce Merlin engine, one of the finest pieces of engineering ever produced in Britain, capable of delivering over 1,000 horsepower. On paper, the Spitfire was everything a modern fighter needed to dominate the skies. But the British government made a decision that would nearly cost them the war. They fitted the prototype Spitfire with a fixed-pitch, two-blade wooden propeller, the same technology that had been obsolete since Caldwell's breakthrough in 1933. Why? Money. The Treasury wanted to save costs, and variable-pitch propellers were expensive, so they bolted wooden wagon wheels onto a Ferrari and called it good enough. The test results were depressing. The Spitfire was sluggish on takeoff. It climbed slowly. Its top speed was respectable, but nowhere near what the Merlin engine was capable of producing. 40% of the engine's power was being wasted, just like the old days, turning into heat and noise instead of thrust. Meanwhile, in Germany, the Messerschmitt Bf 109 was flying with a licensed copy of Frank Caldwell's variable pitch technology. German engineers had recognized the value immediately and paid Hamilton Standard for the rights to manufacture the system under license. Every Luftwaffe fighter rolling off the production line had hydraulic propellers that could shift between fine and coarse pitch. The Germans could outclimb the British. They could dive faster without over-revving their engines. They could use the full power of their Daimler-Benz engines at every stage of flight, while British pilots were stuck with propellers that were efficient at exactly one speed and useless everywhere else. War was not just approaching. It was inevitable. Adolf Hitler had already annexed Austria and Czechoslovakia. He was eyeing Poland. British intelligence knew the Luftwaffe was the most advanced air force in Europe, and they knew why. The technology gap was not in the airframes or the engines. It was in the propellers. Frank Caldwell's invention was sitting on a shelf in America, available to anyone willing to pay for it, while the Royal Air Force was about to send their pilots into combat with one hand tied behind their backs. The Spitfire could have been the perfect weapon. Instead, it was a thoroughbred horse shackled with a wooden cart. But Frank Caldwell had not stopped innovating. He had already moved beyond the two-position system that saved Boeing. He was building something even more revolutionary. By 1938, Caldwell's two-position propeller was the industry standard. It gave pilots two choices: fine pitch for takeoff and climb, coarse pitch for cruising. It was a massive improvement over fixed propellers, but it was still crude. It required the pilot to manually shift gears by pulling a lever in the cockpit. In calm conditions, over friendly territory, this was manageable. But in a dogfight, when a pilot is pulling 6 gravities in a turn and watching tracer rounds streak past his canopy, he does not have time to watch his revolutions per minute gauge and fiddle with a propeller lever. If he dives to escape an attacker, the airspeed increases and the engine over-revs. The propeller spins faster and faster until something breaks. Valves shatter. Pistons seize. The engine tears itself apart in mid-air. If he climbs too steeply, the opposite happens. The engine bogs down, loses power, and the aircraft stalls. The pilot falls out of the sky, an easy target for anyone behind him. Caldwell knew that for the propeller to be a true weapon, it needed to think for itself. It needed to be automatic. He designed what he called the constant speed unit, and it was pure mechanical genius. Caldwell did not just want a gearbox. He wanted an automatic transmission for the sky. He designed a mechanical governor that sat on the nose of the engine, connected directly to the propeller hub. Inside the governor were rotating flyweights, heavy metal balls that spun with the engine shaft. Here is how it worked. The pilot set a target revolutions per minute on a dial in the cockpit, usually around 2,850. From that moment on, the propeller regulated itself. If the aircraft dived and the engine started to speed up, the flyweights spun faster. Centrifugal force pulled them outward, like weights on a string being swung in a circle. This outward movement physically pushed a valve stem, which opened an oil line. High-pressure oil rushed into the propeller hub, twisting the blades to a steeper angle. Coarse pitch. The blades bit more air. The drag increased. The engine slowed down, back to the target revolutions. If the aircraft climbed and the engine started to slow down, the opposite happened. The flyweights pulled inward, closing the valve, and the blades twisted back to fine pitch. Less drag, more revolutions. The system hunted constantly, making thousands of tiny adjustments every minute, always searching for the perfect bite of air. It was a continuously variable transmission for the sky. Whether the pilot was climbing vertically at full throttle or diving at 400 miles per hour, the engine stayed locked at its peak power band. The propeller adjusted automatically, instantly, without the pilot touching a thing. Caldwell had built a machine that could outthink a human in the chaos of combat. The constant speed propeller did not just make flying easier, it made pilots faster, more aggressive, and far more lethal. Every ounce of engine power was now available all the time, in every flight regime. In 1940, the British Royal Air Force finally realized what they had been missing, and by then, it was almost too late. June 1940. The Nazis have conquered France. Norway has fallen. Denmark, Belgium, the Netherlands, all crushed in weeks. Adolf Hitler's Wehrmacht is standing on the French coast, staring across the English Channel at Britain. The Luftwaffe has over 2,000 aircraft ready to sweep the Royal Air Force from the skies, and Hermann Göring has promised Hitler he can do it in days. The Battle of Britain is about to begin, and the RAF has a catastrophic problem. Many of their Spitfires and Hurricanes are still fitted with the older two-position propellers. Some squadrons are still flying with fixed-pitch wooden propellers. Against the Messerschmitt Bf 109, which has fully automatic constant-speed propellers, they are sitting ducks. British pilots know exactly what this means. In a dogfight, when a German pilot wants to dive away and escape, he pushes the nose down and opens the throttle wide. His constant-speed propeller automatically adjusts to prevent the engine from over-revving. He can use full power in the dive and disappear before the British pilot can react. But a Spitfire pilot with a two-position propeller has to throttle back manually to save his engine. By the time he adjusts, the German is gone. The tactical disadvantage is not subtle. It is the difference between chasing down an enemy and watching him escape. It is the difference between life and ending up as wreckage scattered across the English countryside. On June 24, 1940, just weeks before the major Luftwaffe attacks would begin, an RAF engineering officer made a desperate telephone call to de Havilland's propeller division at Hatfield. He did not go through official channels. He did not file paperwork. He asked a simple question. Could the two-position de Havilland propellers currently installed on RAF fighters be converted to constant-speed operation without a lot of bureaucratic nonsense, starting immediately? De Havilland's answer was yes, easily. They had been manufacturing conversion kits in anticipation of exactly this moment. What happened next was one of the greatest engineering scrambles in history. On the morning of June 24th, a convoy of lorries departed from the de Havilland factory. Each lorry carried conversion kits, tools, and a team of engineers in workshop coats. The vehicles spread out across southern England, heading for 12 different RAF airfields. There was no time to bring aircraft back to the factory. The conversion had to happen in the field, on grass runways, in whatever weather came. The engineers worked in the rain. They worked under canvas tents. They drilled new holes in engine bulkheads to run oil lines. They bolted Caldwell's Governors onto Merlin engines. They were modifying the most sophisticated fighter aircraft on Earth, with hand drills and spanners, often while air raid sirens wailed in the distance. The teams worked 24 hours a day. They slept under the wings of Spitfires. They trained squadron mechanics using a brutal but effective method. Demonstrate one conversion, supervise the second, observe the third. Then move to the next airfield and leave the trained mechanics to finish the work. In 54 days, between June 24th and August 16th, 1940, de Havilland engineers and RAF ground crews converted over 1,000 Spitfires and Hurricanes from two-position to constant-speed propellers. Most of the conversions happened in muddy fields, in the middle of the worst crisis Britain had faced in centuries. And the result was instant. The constant-speed Spitfire could now climb at 7,000 feet per minute when pushed hard. Its service ceiling increased by 7,000 feet, reaching 34,400 feet. The top speed increased by 12 miles per hour. But the real advantage was not in the numbers. It was in the dogfight. Now, when a German pilot tried to dive away, the British pilot did not have to throttle back. He could push the nose down, keep the throttle wide open, and his propeller would automatically adjust to protect the engine. He could stick to the German's tail like glue, following every maneuver, pouring machine gun fire into the enemy until the Messerschmitt broke apart, or the pilot bailed out. German pilots were shocked. A week earlier, British fighters had been sluggish, predictable, easy to escape. Now they were performing maneuvers that should not have been possible. The Spitfire could use 100% of its engine power 100% of the time, in every attitude, at every altitude. That was the difference between survival and going down in flames over the Channel. Frank Caldwell's American invention, installed by British mechanics in a muddy field under threat of invasion, had leveled the playing field just in time. The Luftwaffe did not conquer Britain in days. They did not conquer it at all. But as the war dragged on and bomber formations began flying deeper into Europe, Caldwell's propeller revealed a dark side that nobody had anticipated. By 1943, Caldwell's constant-speed propellers were on every Allied fighter. They were winning dogfights over Europe, over the Pacific, over North Africa. But for bomber crews flying Boeing B-17, Flying Fortresses, and consolidated B-24 Liberators, the propeller had become something far more sinister. When an engine was hit by flak and lost power over Germany, it did not just stop turning, it became a killer. A dead engine in midair does not seize up and freeze. The rushing air hits the flat propeller blades and forces them to spin, faster and faster, like a windmill in a hurricane. This is called windmilling, and it is absolutely terrifying. The propeller is no longer producing thrust. It is acting as a massive air brake on one side of the aircraft. The drag is so immense that it can pull a bomber into a deadly spin, flipping it upside down in seconds. The dead engine is not just failing to help, it is actively trying to destroy the rest of the aircraft. Imagine flying a B-17 at 25,000 feet over occupied Europe. You are already dodging flak bursts and Luftwaffe fighters. Suddenly, your number 2 engine takes a direct hit. Oil pressure drops to 0. The engine loses power, but the propeller does not stop. It starts windmilling, spinning uselessly, creating tons of drag on your left wing. The aircraft starts pulling hard to the left. You fight the controls, trying to keep the wings level, but the bomber is losing altitude fast. If you cannot stop that propeller from spinning, you will lose control and spiral into the ground. Your crew of 10 men will not make it home. Frank Caldwell knew the only way to save bomber crews was to stop the windmill before it killed them. But the air forces on a windmilling propeller are massive. Tons of pressure, trying to keep the blades spinning. Caldwell needed a way to rotate the blades 90 degrees, turning them edge-on to the wind. He called it feathering. Think of it like a knife cutting through water. If you slap water with the flat of a blade, it stops dead with maximum resistance. If you slice through with the edge, it glides effortlessly. Caldwell needed to turn the propeller blades into knives. He designed a panic button in the cockpit, mounted directly above the throttle controls. When the pilot hit the feather button for a specific engine, an auxiliary electric pump screamed to life, bypassing the normal hydraulic governor. It pumped high-pressure oil into the propeller hub, forcing the piston past its normal limits. The blades twisted all the way to 90 degrees. They streamlined. The wind caught the thin edge instead of the flat face, and the propeller simply stopped spinning. The drag vanished instantly. The aircraft stabilized. The effect was miraculous. A B-17 Flying Fortress with 2 feathered engines could still fly. It could not maintain formation with the rest of the bomber group, and it could not hold altitude as well, but it could limp home across France, across the English Channel, back to an airfield in England. Without feathering, those aircraft would have spiraled into the ground within minutes. Thousands of bomber crew members made it home to their families solely because Frank Caldwell figured out how to make a propeller turn sideways. The feathering mechanism became standard on every Allied bomber. It saved more lives than anyone will ever be able to count. The war ended in 1945. The jet age arrived, and for a brief moment, it seemed like Caldwell's invention had become obsolete. But the laws of physics are stubborn. Frank Whittle's jet engines did not need propellers. They used internal turbines to compress air and generate thrust. For the first time in aviation history, the propeller seemed genuinely obsolete. Jets were faster, sleeker, more powerful. They broke the sound barrier. They flew at altitudes where propellers simply could not function. By the 1950s, military planners and airline executives were convinced that propellers belonged in museums, alongside wooden biplanes and leather flying helmets. Caldwell's invention had changed the world, and now the world was moving on. But physics does not care about fashion. Jets are fast, but they are monumentally thirsty. They burn fuel at a ferocious rate, especially at lower altitudes where most of their flight time actually happens. For short-haul cargo flights, for military transports, for regional airlines connecting smaller cities, the jet engine was overkill. You still needed the efficiency of a propeller, so engineers did something brilliant. They took a jet engine and bolted a Caldwell propeller to the front of it. The turboprop was born. Look at a modern Lockheed C-130, Hercules, the workhorse of military airlift operations around the world. Look at the Dash 8 regional airliners that connect smaller airports across Europe and North America. They use massive, multi-bladed propellers with technology that would be instantly recognizable to Frank Caldwell. Inside those hubs, you will find governors, counterweights, hydraulic pistons, and oil pressure lines. The computer controls the system now, feeding data from dozens of sensors. But the fundamental mechanics are exactly the same as what Caldwell designed in 1929. The gearbox of the sky never went away. It just got smarter. Frank Caldwell is rarely mentioned in history books. He did not build the engine, like Rolls-Royce or Pratt & Whitney. He did not design iconic airframes like Reginald Mitchell with the Spitfire or Clarence Johnson with the P-51 Mustang. What Caldwell built was the link between them. He was the man who realized that raw power is absolutely nothing without control. You can have the most powerful engine ever designed, but if you cannot transfer that power efficiently, you have built an expensive paperweight. Every time you see an aircraft take off, watch the propellers. Watch them bite into the air, pulling the aircraft forward, lifting tons of metal and fuel off the ground. That is Frank Caldwell's invisible hand, shifting gears so we can touch the clouds. The engine provides the muscle. The wing provides the lift, but the propeller provides the grip. And without grip, you are just a car in fourth gear, screaming and going nowhere.